Welcome viewers. In this second stage of design of 220 kV double circuit transmission line tower design using Autodesk robot structural analysis in Indian standard, we are going to discuss about the slenderness check, member design and deflection check. Let me go to that Excel calculation on slenderness check. In the left hand side you can see an Excel sheet which is developed for explaining this slenderness check. In the right hand side you can see a PDF file ISC 802 part 1 section 2, where we need to find the limitation and the consideration to calculate the slenderness. So for checking this maximum slenderness, that is a limitation in slenderness as per IS 802, we need to refer class 6.3 of IS 802 part 1 section 2. So here you can see in the right hand side file, PDF file. So limiting values are KL divided by R. K is the effective length coefficient and L is the length of the member. R is a radius of gyration. So here there are some 4 classifications are given. One is for leg members, ground wire peak member and lower members of the cross arm in compression. The limited slenderness is 120. For other members carrying computed stresses, like for example bracing, primary bracings which used to transfer the loads to the main leg, we need to consider 200 as limiting slenderness. And for redundant members or secondary members which is carrying a very nominal stresses, we need to consider 250. And finally for members which are used to carry only the tension forces, we can consider 400 as a maximum slenderness limit. So after fixing this maximum or limiting slenderness as per the class 6.3, so we need to find the actual slenderness of each member. So for that we need to refer class 6.1 of IS 802 part 1 section 2. So here you can see in the right hand side PDF. So there are 8 number of member types are here are listed here. According to that, the value of KL divided by R, that is slenderness value. How to calculate the slenderness value are given here. So for example, for leg sections or joint members bolted in both faces at connections, we need to consider L by R as a slenderness, but that should be limited to 120 as which was described in class 6.3. You can see in the Excel calculation. Similarly, for members with the concentric loading at both ends of the unsupported panel, the same case we can consider as L by R. In that case also, that 120 is a maximum limit of slenderness. So similar like for members with the concentric loading at one end and normal framing eccentricity at the other end of the supported panel. So for that we need to consider this case. Instead of reading to this text, we can also having a virtual format like pictures. So for that we need to refer annexure B of this code. So here you can see in the right hand side annexure B are there. So for that there are definitions are given under various cases, like for example member using symmetrical bracing. So for symmetrical bracing, see if you can see in one side the bracing is going in the same direction, in the other side, other face, you can, which is perpendicular to the face, the both the bracing members in two faces are connected in single node. So likewise, if you see this bracing and other side bracing are connected in the same node. So if it is this if this is the case, then the measured length of the main leg is L, which is a vertical length here. So this is a maximum length in this entire span, you can see, because this is smaller than the mid one, and the largest, that is largest span is this top one. So only this top member we need to consider. If all these 3 vertical main leg are having a same kind of section. For example, if it is IS 100 by 10 here and here and here, means we need to consider the maximum length of the panel. So here we can consider directly the length which is measured here as L and divided by RVV. RVV is nothing but is a radius of gyration in principal axis. So here you can see in the picture X and Y are the plane of axis of the angle member, whereas V is a plane of principal axis. So we need to consider RVV. So KL by R equal to L by RVV. So this is a equation we need to find out for the main leg. Bracings with and without a secondary member, there are certain methods to calculate the slenderness are provided here. So again here we need to consider the length as per, for example, in B 8.2 cases, we need to consider AC, A to C, this span divided by RVV, RCB divided by RV, R. So likewise there are various parameters are given. So in all these cases we need to consider whichever the maximum slenderness. So these are applicable for the bracing members. So likewise there are various pattern. For check for slenderness, we need to have a tabular format like this. In the first column we need to add the type of member as we discussed here in this table as per class 6.1 of IS 802 part 1 section 2. Next one is we need this column filled with the group of members which we had assigned in our model, structural model in robot. This one is a member type, whether it is a leg member or primary, secondary bracing or tension members. So this is as per that drop down list is as per this list here showing, and this column is for section chosen for modeling, and these are the member span which we need to find out from the model, and these are IVV or IYY type we need to select from this drop down list according to the case which is shown in that annexer B of IS 802 part 1 section 2. So like this we need to find by visually, and we need to fix this IYY or IVV, whatever is applicable for this member, and according to that I value will be considered by calculating the section properties as per this drop down list selected here, where you can see find here that Excel table format here. So that will pick from here. Accordingly this I value is calculated with that span, and this actual slenderness, this calculation will done as per this formula listed in class 6.1, which is followed by that VLOOKUP format, and this is a limiting value as per this type of member. This will pick from here. So that first type of member column is depends upon the connection of the member and the restrictions and the loading parameters, and this type is a geometrical type. Also the usage of slenderness will calculate by default. So this type we can decide after filling this group, member type, section chosen, and the span, and this all those parameters. So first let we fill this group. So go to this robot model which we have developed already, and click the table icon in the right hand side. So select this groups of objects, click OK. So here in this table you can see lot of all the group name. You can just select and copy by pressing Ctrl C and paste here. So all the group name are pasted here, imported from robot. Now we know these are the leg members, and this also leg member. So this is also leg and this is also leg, and CABB. So we can select from here. CABB is showing a bracing member. So this could be a primary bracing. Now we filled member type for all the groups. So quickly we can check in this robot structural model. So click this member selection icon, click group. So based upon the Excel sheet in the left hand side, you can see that B leg 1 to 4 are leg member we had assigned. So you can select here. Next is C leg 1 and 2, 3. So you can select here by pressing Control on the keyboard, so that it will be select continuously. And the P leg 1 and 2 also we had chosen as a member type as leg. And finally XPC and XTC, cross arm top and bottom card, we had select as a leg member. And after selecting this by pressing the Control key, click here the double up arrow, so that you can see in the windows all the leg members are selected. So these are the leg members. So cross arm, cage, body and peak leg members are selected. So these are the member type, we can call it as leg. And quickly we can also check what are the secondary bracing. So secondary bracing are hip, hip, and here XHB, YHB. So we can also select here hip, XHB and YHB. Again click this double up arrow. So you can see here in the window the blue color highlighted members are secondary bracing. So remaining all this except the leg and the secondary bracing, all are we can assign as primary bracing here. Next we need to fill this section chosen. So for that we need to select one by one the group name in this drop down list. So B leg 1, you can see here in this object inspector in this table under properties section, 150 by 150 by 15 is a assigned properties for this. So we can select from this drop down list. Accordingly we need to do it for all the member groups. So until this YXB5 we need to fill this. So 75 by 75 by 6 is there. So we had filled those. So next we need to fill this member span and the type of radius of gyration. So before going to fill this value, we need to check our model whether it is having a stability to withstand the structural loading. So let me do that first by applying the calculation or analyzing process in robot structural model. Then we will update this member span and the type of radius of gyration, and finally we can able to check the slenderness. So we had already applied all the loads and load cases with our previous stage of video, that is first stage video. We had added this and we had seen this how to apply those loads and how to apply the load combinations also. So after applying all these loads and load combinations, we need to click this calculations icon, which is just below the main menu. So you can see here it is showing some instability of type 2 detected at node 79. So likewise there are a lot of nodes which is showing as a instability. So let we see what are those instability. So after clicking this blue color line, text line. So it is showing where are the instability occurs. So generally while doing this kind of a big transmission line tower, we used to find some instability error that what are the software we are using in that it usually will show, but it is not a minor thing. We just like that, we should not ignore this. We need to check what is the main problem in that. So first let we come with this. So you can see here. So before that we need to click here in the bottom node numbers. Let we can see the node numbers to be visible. So here if you come to this model, and you can see here this member is connected with some node which is mentioned as 148, but this node is somewhat isolated from the main node which is 13. This is a error which while we have done while doing the model, so it should be corrected. So for that we need to select this member which is wrongly created the node and go to that object inspector. In that below left side you can see there are two nodes, node 1 and 2. In that node 1 to be corrected, as instead of 148 it should be 13. So I'm just entering using my keyboard. It will ask, you can click yes, and you can delete this unwanted node. So similar like here also you can see the same kind of member is created in separate node. 147 should be changed to 15. So delete this node. So again if you click here this calculation message, it's again showing, so there is no instability node is showing here. So now if you are coming here to here next level cross arm, so here also you can see that this member is connected to a isolated node 130, that should be exactly corrected as 9. So this may be possible while doing this kind of error, may be possible while doing modeling, so that we need to correct it afterwards or during this analysis. So likewise if you see another one instability is showing here in the bottom cross arm, so that also we need to delete it and do like this which we did for other two cross arms. So this would be 5. So now we have done all the at least knowing cases. So now again we can click here calculations, and again it is showing instability of type 2 detected at node 80 and 81. So now only there are two nodes are highlighted here in the calculation message. So what are those nodes? Let me see. Yeah, it is in the bottom bracing. To solve this instability we need to check the bracing pattern which we are having. We can close these calculation messages. So here you can see here it is mentioned, it is showing as a V inverted V bracing. This kind of inverted V bracing will cause instability because that in top direction there is no connectivity of the bracing, so that the force cannot be distributed equally. So there will be instability for these hip bracing members and its nodes. So we need to overcome this. So we already know that we already created a lot of members and created the member grouping, member profile, all those parameters. So we should not disturb this grouping system and the property system which we had provided. But we need to change this inverted V bracing into X bracing, so that this member will connect from here to the leg member exactly, and this member in the left hand side will connect to the right hand side main leg member. So such a way that we can eliminate this hip bracing system, and we can have it in a later stage for a redundant member to reduce the bracing length. So let we see that. So for that we need to select this up to this portion alone. we are going to make this portion alone to be a expressing by changing this inverted V bracing arrangement. After selecting this, click here in the edit new window icon just below the main menu. So we know that this member should be connected. So one side it is connected to node number 4, other side instead of 77 it should connected to 39. So we are not going to delete the member and do the expressing. We are just utilizing the same member by changing its node parameters. So instead of 77 it should be 39. So first time it will ask that pop-up menu yes or no, because it had done the calculation and the results also showing here green after analyzing that. But now when we are changing that, this result will change into yellow color. So for that reason it will ask some one pop-up menu will come. So that time we need to give yes. And now we need to select this member and change this 77 to 40. So here the 77 should be changed to 40. So one side we had applied that expressing. So likewise we need to do the all the around members in the two level, that is for this member, this leg level and this leg level we need to do it. And after completing that we need to delete this bracing, hip bracing, which is showing here. And even in the top view we are having this lateral bracing system. So this also we need to delete it. So why? Because this bracing member is not required, this secondary bracing member is not required to show here in this model. Always it will it will show the instability. So what we can do is, in practice while doing the detailed drawing, we can add this hip bracing and the diagonal hip bracing to the drawings. Instead of adding to this structural model for analysis, we can add it later. So we need to do like this. This is a model. Now it is updated for the X bracing instead of inverted V. You can see in these directions, right and back, front, left, front, everywhere. And also the hip bracing which was shown here, these two hip bracing are removed. So we can also check that in group. Click this table icon and tick, select these groups of objects. So you can see here in that hip and the diagonal secondary bracing for hip X HP and Y HP are deleted. There is no node numbers you can see here, member number you can see here. So it is left blank, that member list for those hip bracing and its diagonal bracing. So now I am clicking here the calculations icon, which is just below the main menu. So there is no instability error. Yes, now our model is perfect, there is no instability. Next we need to do member design. So go to design in the main menu, click steel members design. So here the load combination are listed here under ULS. There is no SLS case for member design, and all the member are listed here. You can also click here and select all and close so that all the members will be listed here, and click here the calculations. Now the calculation is in process for design of member for their utilization ratio. So that message here you can see here, it angle is not checked for buckling. Yes, it is not required to check for buckling because these are angle member are not subject to buckling. These are subject to only the axial forces, tension and compression, as these are designed as a truss member. And the 440 members are made from angles defined in the system of axis parallel these members are not checked for, yes, of course, it should not be checked for buckling. And coming to the results, the ratio, utilization ratio, it should be less than 1, and here the green color icon should mention with OK. Then it is stated that the member is safe. So if you come down to see all the member verifications, yeah, here from the 144 there are some members are showing that yellow color and red color. Yellow color with this quotation, this symbol is means that this member is in instability, and here 145 is in red color. So this means that member is not safe for its utilization ratio. So here in this utilization ratio you can see it is 1.17. Also here in that 147 the member which is having the utilization of 1.07, it is 107%. It is more than the utilization capacity. So here also some members are showing instability, that is yellow color icon, and red. So first we will find out, we need to find out under which group these members are falling. So for that click this table icon and click group. So before that go to this steel to start and click this table, group of tables. So you can see here the group of tables. So it is 144, 145, 146, where it is starting is, it is from YXX. So we need to change this member size for this XXB1, YXB1 to 5. Instead of 60 by 6, it should be 75 by 8, so that this red color can be removed. So let we do that. So for that you can close this, cancel, click this table, no need, click here this icon which is showing as a member selection, go to group. So in that group we need to select this XXB1 to YXB5, click this double up arrow so that all the bracing members are selected. So here go to that object inspector showing the property table, under section select here 75 by 75 by 6, and the performed operation will cause the changes in the database. So here that green color which is showing that results in FEM is available will change to out of date after clicking yes. So that is what we want. So here you can see the results. So again we need to run the calculations here in the, so now the calculation had done. So here you can see that green color is showing with the FEM is available. Go to design, steel members. Now again you can click this calculations. So now the calculation is performing. So these are the members, again the same message is coming. So these are the members are stating OK or pass, and here you can see that yellow color which is showing the instability of the member, and coming down there is no red color but yellow is there. We should not ignore that yellow which is stating that instability also, even though it is the value of utilization ratio is less than 1. Say for example it is 0.46 and 0.24. So these are less than 1. We should not ignore this simply like that. So you can close this, again cancel, come to that model view. So here if you see here, double click this, go to click this code check. Here you can see the slenderness value, which is showing 274.66. So this is a main reason that member is showing instability. Why? It is because as per the code norms of IS 802, it is stating that for primary, all the primary bracing should have 200 as a limiting slenderness, but here it is exceeding that. So because of this exceeding slenderness value, what it will happen is that angle member will subject to more restriction to have the compression loads. So because of that, there will be instability in that angle member. Even though that member is capable to withstand that, but it is a failure in slender. So we need to add the secondary bracing to reduce its length. So this anyway we are not going to do in the model. If we are doing the same thing in the model, like adding a redundant member in between this node, center node, and connecting to the main leg, and so we need to, generally it is practically we need to do that in detailing, but not in this model drawing. So we need to add a member here by connecting the leg and the mid of the bracing member, cross bracing member. Similar like this direction also we need to add one. So again this both the members should be tied with the hip bracing in other direction, which will be tied to all the four leg in the top view, so which we had deleted already. So the same pattern we need to add it in a detailing stage, not in this model stage. So what we can do is we need to do it in the modeling stage to reduce the slenderness. It means to reduce the effective length. So this big span of 6.37 meters should be reduced to a certain length as per the practical detailing by adding a member in between. So for that we need to go to design, steel member design options, click here code parameters. So we need to create a new kind of a member type specifications. We can call it as X bracing, and as we see we are going to add a member in the detailing stage at the mid span of the cross bracing, which is to be connected in the other end, it is to be connected with the leg member. So it means 50% of the length we are going to reduce, but as for the critical concern, we can reduce at least 1/3 of the span. It means we are going to apply, instead of considering the one whole length, 2/3, that is 0.67 we are going to consider. Even instead of 50% we are considering 67%, that is 2/3 of the span. Click save. So it is saved now. Now what can we do is, we know that from this taperness, the mainly this leg members are having huge span, huge length, so we need to break it by applying the hip bracing or redundant member. So select this member selection icon, click here and click group, select this X, YX B1, YX B2, and first this 3 1. So this 3 will come up to here. So again we need to click this 4 and this 4. So up to this bottom we had selected, and click here this XBC and apply. So now we can go to design, steel member design. So run this calculation. So these members are passed. All the members are maximum passed. Yes. Now there is no instability error. There is no failure of member. So here all the members are passed. So you can see here. So now this calculation we can save it here. So now we can save and close. So how this is possible in practical, let we see. So before that, this node view is not required now. Now we can move here. So we can insert here one bracing redundant member in practical and up to here. But for here this level, it's not required to add a hip bracing or a redundant member. Instead of that, we can fix here with a bolt of these two X bracing, keeping a back to back to each other. So one bolt we need to provide here, mid bolt, so that the entire length of this X bracing get reduced to 2/3. So that is what we had done, and the entire member are pass. So we know from the design icon or design report that all the members are safe. That is, all the members are having the utilization ratio less than 1. So in order to give for the documentation purpose, we need to give that maps or in detail about the view of utilization ratio. For that, we need to click the results, click this maps on members, click the design tab, select ratio and click apply. So you can see the map or a color representation for the members subject to the utilization ratio, and click scale. Generally that red color means we can have it which the utilization, if it is exceeding the limit, that is 1, we can have it a red color. In between 0.3 and 0.6, if the member is having the utilization ratio, then the color should be in yellow color. So click this apply. So you can see here in the window the members which are subject to, which are having the utilization ratio from 0.3 to 1, it is in showing in green color, and if it is less than 0.3, it is in yellow color. We can also change the color indication if required. Say for example, if you want this pink color, you can select here and click apply. It will show like this. So it depends upon the requirement of the documentation we can give. If we want that values to be displayed on the window for taking the snapshot and submit for the documentation, click these parameters and click labels and click apply. So you can see here n number of values of utilization, depends upon the member and marking, the part marking of that individual members and their values. So if it seems to be a messy, you can select the text option in the parameters and click apply. So you can see a good looking window. This you can take a screenshot or having a option to capture the screen, and after capturing this, it will move to that separate page like here in that file and print out composition. So here it is, you need to add this and preview this and print. So this is what the documentation of this utilization of each members. Now let's we go back to our slenderness check. So in the slenderness calculation which we had did earlier, so we already changed this bracing due to that instability and the safety or bearing, load bearing. So if you check here that it is a 75 by 75 by 6, so we can update this section detail for this all the bracings. So now we need to measure the dimension or span of each member under the group. whichever having the maximum span. So for that we need to use this tools dimension line. So now all the dimension are marked here in that model window. You can see here from the first main leg, that is P leg 1 is start from 3-meter span. So we already discussed that we need to break this due to that slenderness. So this 3000 divided by 2 we can consider, or as we considered as a 2/3 of the span we can consider here, so that the usage factor of this slenderness 157. Anyway, we need to fill this span. So based upon this measurement, already these dimensions are filled. Let me check only the failure cases. So here that type, if you want to fill, we need to look into here. So these are for all the leg sections are joint members, we need to consider the type A. So these are the leg member, we need to fix at type A, and wherever the leg is coming we need to fix as A, and this is a leg here A. And coming to the primary bracings, so this is a case we need to consider member unrestrained against rotations at both the ends of the unsupported panel, because that bracing, whenever if you look into that image window, so the bracing, one flange is used to connect with the main leg, but the other flange is free. So one side it is unrestrained, so we need to consider this E value. So for all the primary it is E. For secondary member we can consider the H type, that is redundant members, whereas the slenderness ratio shall be L by R. So H and H here for hip XHP and YHP group. Similarly, for type of radius of gyration, we can select from this what are the cases applicable. Coming to that leg member, if you see here, all the leg members are concentric loading only, so we can consider span divided by RVV. And for bracing system, we need to check these pictures. So based upon this value, AB is the distance of bracing, AB divided by RVV, that is from the fixing point at the mid of the junction. If you are providing any connection or any bolt here, we need to consider AB is the span divided by RVV. And in this case, if we are providing a 3, breaking the panel into 2 by providing a 3 bracing in between the redundant space, then we need to consider the formula like this. So most of the case in our calculation, RVV is playing, RVV is applicable for our case, so we can have it as RVV. So now look into that slenderness failure members. So if we come to this CABB, let me go to the model. So CABB is a bracing member for cross arm. So you can see here, this is a bracing member for cross arm. So here it is failing. If the dimension, if you are measuring here, it is coming 2190. So for that we need to change this to higher dimension or higher section. So here it is passing in slenderness. So in our model we need to change this. In our robot model we need to change this member profile. So select this, CABB. So this CABB will be 60 by 60 by 6. So likewise we need to check on both the aspect, in slenderness aspect, also in axial tension or compression bearing capacity. So this robot structural analysis which we had did earlier will give you the member is safe against the tension and compression forces. But we need to check the slenderness as per the IS 802 cases. Accordingly, we need to change or we need to increase the member sizes. So it is a two-way of analysis we need to do. So similar like CATB, if you are looking into that CATB, it is a top card member of cross arm. So even for that also this is failuring. So we need to change this section to 60 by 60 by 6. So now this is passing. So next one is that CATB. So this is already 60 by 60. So, but yeah, now it is pass. And CAXTB. This is CAXTB is a cross arm at cross arm. It is a cross bracing at the connection between the tower and the cross arm. So for this, instead of increasing the member size, we can also do one alternative measure. You can give you can connect this two cross member with a single bolt of 12 mm maybe. With that, this entire length get breakdown, whereas that unsupported length can be reduced from 2830 divided by 2, so that this member can pass in slenderness. So now the next slender failure member is PLEG2, peak leg member. So select this. Here it is 80 by 80. So let me check that whether it is safe in any other section, higher section. For 100, 110 it is safe for slender. So we can fix that here in the robot structural analysis also. So next failure case is PTBB. So for PTBB, if you see, it is a tie bracing for peak area. So let me check with that whether if it is a 60-60 angle, yes, it is safe. So next coming to that XTC, cross bracing top card. So that 60-60 is not safe. So we can go for 70 by 7 or 75 by 6 we can go. So now it is safe. So for XXB1, so XXB1 is this case, which is having a span of 6,240. As we discussed earlier, we need to break this. If we are going to break it by half, like 2, again it is 106. So what we can do is we can divide it by 3, that is 2 segment of bracing. So likewise in the B 8.2, so there are 3 bracing, redundant bracing in between this main bracing. So the formula to calculate the slenderness is the span divided by RVB. So this is what we had done here. Next one is XXB2. So that is also having a 540. So if we are going to divide this by 2, now it is safe. So then for this bracing alone we can have like this B 8.1. We can fix one redundant member here to connect with the main leg, so likewise. And coming to that next level of bracing, XX3, which is here, having the span of 5 meter. So here also we need to provide a, it should be divided by 2. So instead of providing a leg member, what we can do is we can provide a bolt, a 16 mm bolt here in between these two X bracing, cross bracing, so that the entire length can be break and the unsupported length can be divided by 2 or some extent. So by that way we can reduce that slenderness. So similar procedure we can apply for this span also. So it is 2500 and here it is 3800 divided by 2. Again this also pass. So all this XB1, YB1 up to XS B5 are same for Y direction also. So now all the member are safe in slenderness. So now we can remove this dimension line which are not required now. Select all and press delete on the keyboard. So now press this. You can see here the result icon which is showing yellow color. Click here, result. All members are passed through in analysis and go to design, steel design. So before that you can also remove the old record, delete it and press calculation. So the calculation is done again with the revised section. So now you can see all the member are pass. So with that member design and you can also save, slenderness check is get completed. Next one we will see the deflection check. So before going to check for that slenderness for this kind of hip bracing and the redundant member, we need to do it as per the detailing requirement. If the detailing, if you are going to do as a 3 or 4 or 2 split of the bracings, wherever the hip bracing we need to keep. So accordingly we need to select this material, the section properties and the span of that, so that we need to check accordingly. This same thing we need to apply in the detail drawing, not in this model. So let we discuss about the deflection check. So we can come to that model view. So click here structural model and start. So this is our 3D model. So go to result, click deflections. So you can double click here in that UX, so that we can see the maximum and minimum deflection in UX and UYY. So these are very minimal, only 1.64 mm or likewise. So for every member, if any member is subject to 1 or 1.64 mm of deflection in UZ direction or UXX, it is 0.89. So these are minor, we can say it. It is very low. We can't able to see in our eyes this kind of deflection. Next, coming to that overall deflection or nodal deflection or displacement, click results, click this displacements. So here you can see that nodal displacement. So if you click this, double click this UX, it is showing 45.37. So here in UYY, it is 221.77 mm. So here it is 64.64 in vertical. So it means that the overall deflection, this is nothing but the overall structured displacement. So how to fix that limitation? So for that there is no direct value in Indian standard. For that we need to go with ASC 113. So in the right hand side you can see that ASC 113. In that we need to refer page number 85. So here there are definitions given. Deflection limitations for horizontal members in class C. So our case we are having the transmission line tower. It is a whole tower structure we need to consider. So it is a vertical member. So this 4.1.4.2 is applicable for our transmission line tower to check the deflection. So here the deflection limitation for vertical members in class C structures is given as a horizontal deflection of vertical members should not exceed 1 divided by 50 of the height of the point investigation above the foundation. So here we need to consider the total height, as we know that from our model it is 32 meter. So 32 divided by 50 will come around 640 mm of deflection. So that is a limitation of the deflection, but in our case we are having 221.77 in the robot result. So those deflection are within the limit, that too in the load case 102. So regarding this class C, that type of class definition are given here in this class 4.1.4. So here it is stated that a class C structures support equipment relatively intensity to deflection or standalone structures. So examples are given as support structures for flexible standard conductor buses. Most of the transmission line tower we used to have a flexible type of conductor buses, so that this class C is applicable. Mass for lighting shield and dead end structures for incoming transmission lines. So these are definition is given for class C. And if you refer to class B, so these are applicable for equipment such as CTs, PT and CCVTs, station power transformer, hawk sticks, switches or horn fuses. And class A is definition is given where there is a operational mechanism like a circuit breaker and a disconnector support. So for this support are considered as a class A. So our case class C to be considered. So for class C, deflection limit is 1 divided by 50 of the total height. So we can conclude that we are safe in a deflection also. So that 102 case is a reliability with the conductor deviation case. So we can also see the result of structural behavior due to the deflection. Further, to go to results, diagrams for members, click the deformation tab, select exact deformation for members. If you want, you can also select a color as per your wish, and here type that 1000, that is for 1 meter. Click start. So now you can see the deflection of the critical load case 102, that is a reliability with the conductor deviation. So with this we can end our stage 2 design of 220 kV transmission line tower with IS 802 loadings. So now on the next final stage or stage 3, we can talk more about the connection design about the transmission line tower. Thank you for watching. Look description for more related video. Subscribe to this channel for more updates. Thank you.